Hi, it's Double O Pi, your undercover chemist here. Today we're going to talk about how to balance a nuclear equation. Before we do that, I want to start by reviewing isotope symbols. So isotope symbols have three different parts. First of all, they have a group of letters which stands for the element this is an isotope of. And then they have two numbers over on the left. The lower number is what we call the atomic number, and that's equal to the number of protons. The upper number is what we call a mass number, and that's the sum of all the particles that have substantial mass in the nucleus. So that's the number of protons and the number of neutrons. We're going to use those isotope symbols to represent what happens in a nuclear reaction. So let's start out by looking at some of the basic particles that you find in nuclear reactions. We're going to start with a neutron. So a neutron is represented with a symbol N, and we're going to write it with an isotope symbol, even though it's not really an isotope. So, question, how many protons in a neutron? That's a silly question. Of course there are no protons in a neutron, it's just a neutron. And so it has an atomic number of 0. What's the mass number of a neutron? Or in other words, how many protons and how many neutrons are in a neutron? Well, of course we know there are no protons in a neutron, but there is one neutron in a neutron, and so it has a mass number of 1. So that's our isotope symbol for a neutron. Now let's look at protons. A proton is represented with the symbol P, and let's write this as an isotope symbol, even though it's technically not an isotope. How many protons in a proton? Well, there's one proton in a proton, so atomic number is 1. What's the mass number of a proton? How many protons and how many neutrons are in a proton? 1 proton, no neutrons. So there's our isotope symbol for a proton. What would happen if you took a neutron and a proton and you put them together? That's a very simple reaction, and that's what we're going to use to learn the rules of how to balance a nuclear equation. The basic principle of a balanced nuclear reaction is that the sum of the mass numbers on one side of the reaction will be equal to the sum of the mass numbers on the other side of the reaction. The sum of the atomic numbers on one side of the reaction will be equal to the sum of the atomic numbers on the other side of the reaction. So I have put up a number of steps, and rather than read them directly to you, we're going to work through our example problem using the steps so you understand how they're applied. So what particle do you get if a neutron and a proton combine? The first step is to add the mass numbers on the left side of the equation. The mass numbers, remember, are the upper numbers. Here they are. We have 1 and 1. 1 plus 1 is 2. And our second step tells us that we're going to add some mass number, our unknown mass number, such that the sum of the mass numbers on the right-hand side of the equation is equal to the sum of the mass numbers on the left side of the equation. In other words, our mass numbers on the left side add up to 2, so our mass numbers on the right side also have to add up to 2. Now it's very convenient. We only have one thing on the right side of the equation, and so it must have a mass number of 2. Now let's look at the atomic numbers. Add up the atomic numbers on the left side. Well, our atomic numbers on the left side, we have a 0 and a 1. 0 plus 1 is 1. Now we're going to find the atomic number of our mystery thing, and that has to be equal to the sum of the mass numbers on the left side, which is 1. Okay, so now we have something which has a mass number of 2 and atomic number of 1. So now we just need to find the symbol for what that particle represents. And we could do that by using the periodic table. Our atomic number is 1. What has an atomic number of 1? Hydrogen. So if you put a proton and a neutron together, you get an isotope of hydrogen that has an atomic number of 1 and a mass number of 2. Okay, now we're going to talk about a beta particle. Beta particles were discovered long before we knew about what particles make up an atom. Well, it turns out that a beta particle is an electron in the nucleus. If you know anything at all about the structure of the atom, you might say, hey, electrons don't belong in the nucleus. That's not where we find electrons. Well, it turns out that if you take a neutron, you can split it and make a proton and an electron. And we can use this knowledge to determine what the symbol for an electron should be. Okay, so on the left side here we have our neutron that's turning into a proton, and this thing, this beta particle, that we don't know the symbol for yet, but we can determine it using the rules of balancing a nuclear equation. So let's start by adding the mass numbers on the left side, and that's extremely easy because we only have one thing on the left side. Our total is 1. Now we're going to add something on the right so that the total mass numbers on the right equals our sum on the left side of 1. So basically what we have, we're looking for whatever is going to make this equation true. 1 equals 1 plus what? That's actually pretty easy. That's 0. So whatever this beta particle is has a mass number of 0. Now let's figure out its atomic number. On the left side, our atomic number adds up to 0. And we have to find something such that 1 plus that thing equals 0. What is that? That's minus 1. 1 minus 1 equals 0. So we could write a beta particle this way using the Greek letter beta and our 0 and minus 1 mass and atomic numbers. Or since it's an electron, we can write it as 0 and minus 1. And then you can see here's the symbol for an electron, an E with a minus sign showing that it's got a negative charge. Another particle that you see in nuclear reactions is a positron. A positron is essentially what we call an anti-electron. What in the world is an anti-electron? Well, as it happens, it's a particle that has the mass of an electron, which you may remember is not very much, but has the opposite charge. That's why it's an anti-electron. It has a positive 1 charge. So normally when we think of a nucleus, we only think of protons and neutrons. Where do positrons fit in? Well, as it turns out, if you take a proton, you can split it and make a neutron and a positron. So what is the mass number of a positron and what is its atomic number? We can once again figure this out by using our nuclear equation balancing. Add the masses on the left side, 1, since there's only one thing on the left side, and then that has to equal 1 plus whatever the mass number of a positron is, and that is going to be 0. So you could see this does still have the same mass as an electron or a beta particle, which we looked at earlier. Now, what's its atomic number? Our atomic numbers on the left side add up to 1, and that means that our atomic numbers on the right side must also add up to 1. So 0 from the neutron plus something equals 1. That something is going to be 1. Our atomic number is 1. And you can see now that this is exactly the opposite of the electron or beta particle, which was 0 and minus 1. Now this is 0 and plus 1. Okay, so we write a positron this way. We can write it as a positively charged beta particle, so the beta symbol and a plus. Or we can write it as an anti-electron, so there's our E for electron, but without the negative charge symbol. Both of these can refer to a positron. The final particle that you frequently see in nuclear reactions is an alpha particle, which we write as 4,2 alpha. Now, once again, the alpha particle was discovered long before we understood much about the nature of the atom, and this is actually a nucleus of an atom. Which atom? Well, it's the element that has an atomic number of 2, which is helium. So this is essentially a helium nucleus. Doesn't have any associated electrons. Now, if you look in a book and you're looking for the products of a nuclear reaction in the book, you might see things like gamma rays. These are energy emitted in the form of EM radiation, and as a result, they don't affect the atomic number or the mass number, so I'm not going to include them here. You might also see this symbol, which looks like a V, which is actually a Greek nu, That stands for a neutrino, which is a particle with no charge. It doesn't affect the atomic number, therefore. And near zero mass, even less mass than an electron. And so that also doesn't affect the mass number. So neutrinos don't really affect the balancing of a nuclear reaction. So we're going to ignore gamma rays and neutrinos for now. That's, if you want to learn more about them, study particle physics. Let's try some problems. All of these problems are nuclear reactions that actually occur in the world. So in this first problem, we have bismuth-211 decaying by alpha emission. What that means is, if you have bismuth-211, it is radioactive, it naturally falls apart, and when it falls apart, what happens is it splits into two pieces. One is an alpha particle, and the other is something else. Okay, what is the something else? That's what we need to find out in this problem. So we first write what we know, which is bismuth-211, and we know that it puts off an alpha particle, 4,2 alpha. You really need to know all of your particles if you're going to get good at balancing nuclear reactions. So alpha particle is 4,2 alpha, a 4,2 helium if you want to write it that way. And it makes something else that we are going to figure out. Let's put our steps up. Okay, let's start by adding the mass numbers on the left side, and this is very easy. We only have one thing on the left side, and it has a total mass number of 211. And now we're going to figure out what we put in that box so that our mass numbers on the right side also add up to 211. Well, 4 plus what is 211? The answer is 207. 207 plus 4 equals 211. Now let's figure out the atomic numbers. On the left side, we have a sum total of 83 for atomic numbers. On the right side, we have to add up to 83. We have two things. 2 plus something equals 83. 2 plus what equals 83? 81. 81 plus 2 equals 83. And now let's figure out what element is created when bismuth-211 undergoes alpha emission. What we're going to do is look at the periodic table to find the appropriate symbol. It's something that has the atomic number of 81. And you look at the periodic table, you find element 81, that's thallium. And so here is our completed nuclear equation. Let's look at another one. Here we have molybdenum-100 decaying by beta emission. And we want to know what it makes besides a beta particle. So once again, this is a radioactive decay where you have an isotope, here molybdenum-100, splitting into two parts. One of those parts is a beta particle, 0 minus 1 beta. The other one is something. We don't know what it is. That's what we're trying to find out. So let's look at the mass numbers first. On the left side, our mass number is 100. We only have one thing on the left side. On the right side, we need to find something such that 0 plus that thing equals 100. Well, that's really easy. That's 100. Now let's do the atomic numbers. Atomic numbers on the left side add up to 42. And now, let's do the right side. We need to find something such that minus 1 plus something equals 42. Now, when I am giving a test, 99% of the time, this is what people get wrong. What plus minus 1 equals 42? A lot of people will say 41. But 41 minus 1 does not equal 42. 43 minus 1 equals 42. So we need something that's 100, mass number, 43 atomic number. What element has an atomic number of 43? Let's look at our periodic table, and it's technetium. So here is our balanced equation. Molybdenum-100 decays by emitting a beta particle and thereby turns into technetium-100. Here's a different sort of balancing problem. Here we're given an isotope that undergoes radioactive decay and forms another isotope. When it undergoes that decay, it's going to also put out a small particle. What is that particle? So here's our strontium-85 that creates rubidium-85. This is something that we geochemists use to help date rocks, so it's a very useful radioactive decay. It also creates some particle. So what is that particle? This is slightly different from what we've been doing in the past, and also it's very much similar. Because we start out by saying, what's the mass number? Mass number of the left side, 85. Mass number of the right side has got to equal 85, so something plus 85 equals 85. That something will be 0. Let's figure out the atomic number of that mystery thing. On the left side, we have a total atomic number of 38. On the right side, we need to have everything add up to 38. So we have to say 37 plus what equals 38? The answer is 1. And so now we know our mass number is 0, our atomic number is 1. What is that particle? That particle is a positron. Okay, we're going to do one last equation, and this one is very different. This is not a radioactive decay equation. This is a fission reaction. And essentially what you have here is you have two particles colliding and forming a bunch of other particles. In the past, we've been doing nuclear reactions where you start with one particle, it splits into two. Now we're starting with two particles and splitting into 2 plus who knows how many others. Let's look at this reaction. When hit by a neutron, uranium-235, so here's uranium-235 being hit by a neutron, so here's our neutron. That's the left side of the equation. On the right side of the equation, our products, we're going to have barium-142 and krypton-91. Those are what's given to us, plus something. We don't know what. Or maybe it's nothing. Maybe these things all add up to be nice and balanced. Let's figure that out. So we start out the same way we always start out. Let's add the mass numbers on the left side, which here is the top because I have a very small screen. Okay, 235 plus 1 is 236. Let's look at the right side. Some of the mass numbers on the right side must equal 236. Right now we have 142 plus 91 plus something, and that ends up being 3 if you do the math. So we need something that has a mass number of 3. Let's do our atomic numbers. On the left side we have 92 plus 0, so that's 92. On the right side we have 56 plus 36 plus something. 56 and 36 adds up to 92, so we are just going to have 0 left over. And then we have to find an appropriate symbol for this. We don't know anything, we haven't seen anything that has a mass number of 3 and an atomic number of 0, and the periodic table won't even help us with an atomic number of 0 because it starts at 1. Well, where can we look for inspiration? If you look here at a neutron, you see a neutron has a mass number of 1 and an atomic number of 0. So if we had 3 of those, that would balance our equation because we'd have a total of 3 mass numbers and a total of 0 atomic numbers. So that's what happens in this reaction. If uranium-235 is hit by a neutron, it splits into barium-142 and krypton-91, and it makes 3 additional neutrons. And that's actually something that can happen in a nuclear reactor to form a chain reaction. I hope you've enjoyed this video. Please check my YouTube channel for other problem-solving videos. Thank you.